Welcome to the training module for Bourns' latest addition to its fixed resistor product line. This training module will cover the new CSS series of current sense resistors. Bourns' fixed resistor product line can be categorized into 9 different resistor technologies. The new CSS series of current sense resistors is categorized under the current sense technology type. Many of the model families in the Bourns fixed resistor product line use thick film technology on a ceramic substrate. While this technology is ideal for high ohm resistors, it becomes unsuitable for low ohm resistors. To achieve resistance values lower than 20 milliohms, Bourns has utilized an open frame metal element design. This is made of a metal alloy sensing element welded to copper terminals. Current sensing resistors are growing in popularity as electronic circuit designers strive for greater efficiencies. Today, current sense resistors are used in circuits such as current sense amplifiers, H-bridge current monitoring, bidirectional battery load charge control, high voltage sampling, lithium-ion gas gauges, and buck-boost switching regulators. As power supply technologies evolve with the demand for greater efficiencies, so too does the need for accurate current sensing. There are numerous current sensing options available to the circuit designer. These include current sense resistors or shunts that are easy to design in, are a cost-effective solution, and assist with signal accuracies. Other technologies include Hall effect sensors, which typically are higher in cost, and performance can vary with temperature. There are also magnetic options, such as Rogowski coils, which are good in higher current applications, but once magnetized may lose accuracy. A current sense resistor's primary aim is to monitor the current within a circuit. This is done using Ohm's law by measuring the voltage drop over the known resistance value of the current sense resistor. The current sense resistors within a circuit can be used to measure current or detect an overcurrent event and help monitor the remaining power in battery circuits. The critical feature one should look for in current sense resistors is the low resistance value. This is typically less than 10 milliohms and can often be in the sub-milliohm, in other words, less than 1 milliohm range. This helps to maximize the energy conversion in the system and minimize power consumption of the resistor. To ensure that the resistor aids with current measurement accuracy, the current sense resistors typically come in the 1% resistance tolerance range, but can have higher at 5% or lower at 0.5% resistance tolerance ranges upon request. Another critical feature to look for in current sense resistors is the temperature coefficient of resistance, or TCR. This is how the resistance value of the resistor can vary due to the self-heating of the resistor. The new CSS series of current sense resistors has a 50 parts per million per degree centigrade TCR over the ambient temperature range of 20 degrees centigrade to 60 degrees centigrade. This is the relative change of the resistance value due to heating or cooling of the resistor. So, 50 parts per million per degree centigrade means 50 parts per million per centigrade degree. Having a low thermal electromotive force, or EMF, is also an important consideration in current sense resistors because of their low inherent resistance levels. The Bourns Model CSS Series is made from welding copper electrodes to a metal alloy sensing element. When 2 dissimilar metals are joined, a voltage is created, and this voltage is known as the thermal EMF that is dependent on temperature. The CSS series has been designed with this consideration in place. Heat dissipation is another critical concern for current sense resistors, and the new CSS series has been designed as an open frame structure to allow for maximum heat dissipation into the surrounding environment. Bourns' new CSS series of current sense resistors have been designed for very low resistance values and are made from an electron beam welded element to the copper terminals. These sheets are then punched and formed to the required shape and value. Currently, the CSS series is available in 2 surface mount structures, 2-terminal devices and 4-terminal devices. The 2-terminal devices come in 3 different footprint sizes, 5930, 3920, and 2512. The 4-terminal series comes in a 4026 size and has been designed for 4 Kelvin resistance measurement. This slide shows the structure of the part number. The CSS is the part family name. Next is the number 2 or 4 to describe the amount of pins, either 2 pins or 4 pins. Next follows the style, either H or J, to describe the shape of the device. Then follows the product size in the inch system, and in the case shown, it's a 2512 size device. Each model will require a different material to achieve the resistance and power rating, and R and K describes the material specification. Next comes the resistance specification, and the letter L representing the decimal point in milliohms. So L500 means 0.5 milliohms. In another example, 10 milliohms would be represented as 10 LO. Finally, we have the resistance tolerance, F for 1% and J for 5%. Lastly, we have a simplified representation of the production of the Bourns Model CSS Series current sense resistors, going from dereeling to part stamping to material passivation to pre-resistance testing to resistance trimming and singulation, ending with the final marking, testing, and packaging.